Let's look at maxes and mins for number 3 here on the handout. Start with local mins. Have any local mins? I think so. Got a low point along in here, so that would be the location of the local min. So the local min is the function value, so the f of 4, and I think we can figure out f of 4 is that 4? It's a little over 4, isn't it? My drawing's a little bit off. Looks like it's just a little bit higher than, it's called 4.2 or approximation there. Anything else? Yeah, we've got another one here, got another low point. So the function value there, f of 8, will be another local min, right? And that's right on 6, I believe. Well, that's good, 6. Any others? I think that's our local mins. Local max. I don't think, yeah, I've got a couple of those. Got a local max at 2. And that looks like it's also at 6. So the function value at 2 is 6. So f of 2 is 6 is a local max. And then I've also got one here at 7, don't I? Yeah, it looks like 7. That one's occurring right above the local max there is occurring at 7. So f of 7. And we'll call that about, what about 9.5? About 9.5 is what you okay with that? Good? All right. Now, just mention here, as far as absolute goes, anything as far as the absolute goes, because on the absolute max or min, you look for the entire domain or specified domain. In this case, I haven't really specified, so it's everywhere. Is there an absolute max? Is there an absolute point that's higher than any of the others? Well, by implication here, I think this is telling me this is extending, it just keeps going up from there on out. There's not gonna be a max out point there. So as far as an absolute maximum goes here, no, there's not one. Kind of like we have on the other one. And then on the minimum side, absolute minimum, we've got a couple of local minimums, but they're not the ultimate lowest point, right? Because this graph keeps extending out this way by implication. I mean, when it's otherwise specified, but it's just going to keep down, 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 right? There is no absolute minimum. So in this case, we don't have the absolute ones. We got a couple of local maxes and mins each, but no absolute ones. All right? Is that okay? Any question or concern there? All right. Go ahead and finish off the handout here. Do number 4. This one we've got y equals g of x. All right, so just the first quadrant one. Kind of accurately here. All right. So this one's about 3, that's about 6, and that's 9. Here, 5 is right there. And these points up here at 7, and it peaks at about 8. All right, so on the handout, sort of what we got. Okay. So this one has some jumps and breaks. So that I want to do an example of this one to get the feel for a couple of things. All right, any start with local maxes. Any local maxes here? Well, obviously we've got a peak. That'll be a maximum point, right, relative to the ones around it. So that's at, that was at 7. So the way I like to put that, the function value at 7, which was 8, that would be the max here. Any others that we could say local max? Well, there is another one. And it just so happens to occur here at 3, right? Because if you look at 3, there's a point disconnected off of that, jumped up at 3. But remember the definition says you've got a point, the function value at which is greater than the ones around it. So if you look at the function value for this, is it greater than the ones around it? Why, sure it is, right? We've got this one is that function value, the y value is much higher than the ones around it. So that is an absolute max. I'm sorry, a local max right there. F of 3 is 7. So a local max for min could occur also at a discontinuity. We looked at local maxes at peaks, or we haven't done one where we had a corner, but that could also happen. But also at discontinuities, you can have these relative maxes and mins. Now the local mins, that brings up a couple of other interesting points. Local mins. Do I have any local mins? Any points I could say are minimums, locally speaking? Well, let's look at the discontinuity here first. Right here at 6 is, we'll say potentially, what about f of 6? F of 6. Well, f of 6 is up here at 7, right? F of 6 is 7. However, is it a local min, though? To be a local min, it has to be, the point has to be lower than the other ones, all the other ones around it. Well, it's lower than these points, right? But is it lower on the other side? No. There's points lower than that one, isn't there? So that one can't be a local min. So you got to be careful with the jumps. You have to be sure it's lower, for a minimum it's lower than all the ones around it. And here. Now you might be saying, well, what about this point? Well, that point, we don't have an f of 6, so what are you going to call the one right next to it? 5.9? Well, we can get closer to that point, open circle there, go 5.99. And it would be lower by, because it's a little bit lower. Then 5.99 wouldn't be good enough because it'd go 5.999, 5.999, yeah, 5.999. You see what I'm saying? So since that's an open circle, you can't really pinpoint a value that's least there because you can always go just a little increment over. So there's not any minimum here. If it had been flipped here, if I had this and then this, now we're in business. You see what I'm saying? Because then I could say, well, f of 6 here, that looks lower than all the points around it, and it's lower than those points. So if it was flip-flopped, we'd have a local min, but it's not. It's this way, okay? Now, the other thing on the local mins, you might be looking at, what about these points? Well, the problem with those points is we don't know what happens on one side or the other of it. What happens to this side at 9? Or what happens at this side at 0, to the left? I don't know what happens to the left or right, to the right here, to the left here. So for local mins, yeah, you can't say whether those are minimums or not. Because it may very well be that they're not. So you have to be able to look at both sides on a local min because of basically the definition. Okay? Now, so there's not any local mins here. It's a little technicalities there because of technicalities. All right? Absolute though. Well, this is one where this, remember on absolute, we said you could look at just a specified domain. And in this particular case, the specified domain is 0 to 9. So for these, remember on absolute max, you can just, we're only looking at the specified domain, which in this case is specified because of the graph. The specified domain is 0 to 9. So on absolute max and mins, you can do that. In other words, you don't have to think about what's going on the other sides of those for the absolute max and min. Now, for local max and min, yeah, you can't guess what happens. But on absolute max, you're only looking on specified domains if that's specified. Okay. So with that being said, it doesn't really matter what happens out here for these. What do I have for absolute max? What's the highest point that occurs in this domain? It's that point right there, isn't it? That's the top point, nothing higher. So f of 7 equals 8 would be my absolute max. And then the absolute min, do I have an absolute minimum? Yeah. On this domain, what's the absolute lowest point? Right here, isn't it? There's not anything lower than that. So f of 0, that looks like it's about, call it 1 1/4. That's my approximation. It may be slightly different than that, but it looks to be about 1 1/4. Is that okay? Any questions on that? It's a little confusing, especially when you get these specified domains. You can't really just specify a domain for local mins and max. You have to know what happens on either side to call it a local min or a max. But absolute min and max, you don't have to do that. You're just looking on this domain. So anyway, it's a little different. All right. So we've seen a couple of examples of local maxes and mins, and the derivative equals 0, derivative does not exist, are places where those occur. So we'll talk more about that in just a second. Let's if I just have a function let's say f of x equals x cubed minus 3x. Let's make it x cubed minus 3x squared. We can identify those pretty good just by looking at the graph. So, same idea here for just identifying it from the graph. So it looks like this. Yeah, so I've got a local max there. It looks like 0, 0. So the function value at 0, n equals 0. And then our local min, well, it looks like here, minus 3x squared. Looks like it's at 2. F of 2 equals -4. So, very same idea. You just look at the graph and get those. We'll do more details about it in a second. Different piece. Now, if you've got, what would you say on this one? F of x equals cosine of x, or your local, based on the graph there, local maxes and mins there. Cosine, where do those occur? Well, cosine, very cyclical. Starts up here at 1, and then you cycle around like that. So where do the peaks and valleys occur there? Well, you got a peak at 0, then your next peak, where's that at? Well, that's a full cycle, isn't it? Period, 2 pi. And then back here at -2 pi. So basically it's the 2 pi's. It occurs at the even pi, 4 pi, 6 pi, right? So f of even pi's. And that maximum is 1. I guess one way you can say it. But here's, if you want to be a little more precise about it, 2 pi n. 2 pi times an integer. 1, 2, 3, right? That would give it. And then the local bins, where do those occur? Well, here is 1 and here's 1. What is that? Isn't that halfway pi? And this would be 3 pi. So it's the odd pi's. F of odd pi. Anyway, all right. So those, just a couple more examples there.